Hello, and welcome to Rational Functions and Models. Let's start with a definition. A function f, represented by f of x equals p of x over q of x, where p of x and q of x are polynomials, and q of x is not the zero polynomial, is called a rational function. All right, so it has to be a ratio of polynomials. So determine whether f is a rational function and state its domain. So here we see in number 1, I have a polynomial, a quadratic, divided by a polynomial, which is a linear function. So this is a rational function. And if we look more carefully here, q of x is not equal to 0, it tells us how to find the denominator. How to find the domain. We take the denominator and set it not equal to 0. 3x cannot be 2. I'm going to go back up over here and get x cannot be 2/3. It's assumed that x is all real numbers except 2/3 when we write this. We could write instead. Alright, so we could write this in 3 different ways. And one is stating x cannot be 2/3, and it's assumed that x could be any other real number. We could write this in interval notation, where we essentially pluck 2/3 out of the number line, and the rest of the number line stays there. Or we could use what's called set builder notation, and it's the set of all x such that x is not 2/3. So any of those 3 notations will work, and you just have to follow the directions to make sure that you get it correct for your homework system or for what your instructor wants. Determine whether f is a rational function and state its domain. Okay, so x squared plus 1 is a polynomial. However, the square root of x minus 4 is not a polynomial. So this is not a rational function. Because it's not rational, I'm not going to bother with the domain at this point. Alright, now rational functions have a couple of things that other graphs don't necessarily have. First of all, the line x equals k is a vertical asymptote of the graph of f if f of x approaches infinity or f of x approaches negative infinity as x approaches k from either the left or the right. So the graph kind of blows up near a specific x value. The line y equals b is a horizontal asymptote that should have been bolded of the graph of f if f of x goes to b as x approaches either infinity or negative infinity. So vertical asymptotes look at what happens to y near a specific value. So does the graph blow up or does the graph go sharply down? Horizontal asymptotes are looking at end behavior. This is x approaching infinity or negative infinity. So infinity is the far right side of the graph. X approaching negative infinity is the far left-hand side of the graph. Do we eventually settle on a number for our y value, for our f of x? So let's use the graphs given here. We have no idea what the functions are, and it doesn't matter. We can look at the graphs and we can identify some asymptotes. So let's identify horizontal asymptotes in blue. So let's do both of the horizontals first. Now horizontal lines, always y equals. And so we're looking for maybe a spot here where the graph gets super close as we go to infinity, and same value that as x goes to negative infinity, we settle in on a value. And now we have to look at our scale. If this is 10, 2, 4, 6, 8, 10, so a scale of 2. 2, 4, this must be the line y equals 3. And so we say y equals 3 is a horizontal asymptote because eventually that's what the graph settles in on. I happen to choose, let's go with gray. Again, it looks like eventually, that's a horrible line, eventually, long time out here towards negative infinity, towards positive infinity, it looks like once again the graphs, the end of the graph is approaching y equals 3. All right, so that's horizontal asymptotes. Now remember, vertical asymptotes, vertical lines, are where the graph blows up. So as I get super close in here, notice that this graph goes up to infinity. And if I approach this same value from the left, f of x approaches negative infinity. And so we say x equals 2 is a vertical asymptote because that's where the graph blows up or blows up in the negative direction. Similarly here, oh, what value are we getting close to? It looks like we're super close to 2. That was a negative 2. This is a positive 2. And so we'll actually have 2 vertical asymptotes here. Vertical asymptotes, always equations of lines. X equals, so x equals 2 and x equals negative 2. And that was just poor planning on my part. That those are not always the values of the horizontal and vertical asymptotes. I just chose really similar examples for some reason. All right. Now, if we're giving, so that's what they look like. That's what a graph looks like. If we're given a function, how do we find vertical and horizontal asymptotes? To find a vertical asymptote, as long as your function is written in lowest terms, so you've canceled all common terms, to find a vertical asymptote, set the denominator q of x equal to 0 and solve. Every 0 of q of x will give us a vertical asymptote. Now, very important caution here. If k is a 0 of both q and p, then the function is not written in lowest terms, and so this doesn't apply. And x minus k is a common factor. Anytime you have a common factor, this will result in a hole in the graph, not an asymptote. So it's pretty interesting. All right, before we move on, let's identify the vertical asymptote here. The vertical asymptote, I know that each term is linear. They have nothing in common. So I can take the denominator, set it equal to 0, and solve. And I have the equation of my vertical asymptote. So I'm going to do all the vertical asymptotes in green. That's it. So just like we set the denominators not equal to 0 for the domain, we set the denominator equals 0 for the vertical asymptotes. Horizontal asymptotes. We're going to compare the degree of the numerator, let's call that n, to the degree of the denominator, let's call that d. If the numerator has a smaller degree than the denominator, then y equals 0, the x-axis, is a horizontal asymptote. If they have equal degrees, then y equals a over b is a horizontal asymptote, where a is the leading coefficient of the numerator and b is the leading coefficient of the denominator when they're written in descending order. If the numerator has a higher degree than the denominator, there are no horizontal asymptotes, but we might find a slant asymptote. Okay, so we compare. The degree of the numerator is 1, it's linear. The degree of the denominator is 1, it's linear. So my horizontal asymptote will be a over b, where my a is the leading coefficient of the numerator, b is the leading coefficient of the denominator, and we will always simplify our fractions. So y equals 2 is our vertical asymptote. 3's and 2's. I try to keep the numbers small, and so my examples look pretty repetitive. All right, so vertical asymptotes, and we put horizontal here in teal. Now let's do horizontal on this one first. Since the degree of the numerator is 0, right, there are no x terms whatsoever, no variables, so it's a constant term, and the degree of the denominator is x squared, the denominator is larger, so we will have y equals 0 as our horizontal asymptote. That's it. There's no work to be done really for the horizontal asymptote. The vertical asymptote will take their denominator, set it equal to 0, and solve. Remember, when you take the square root, you have to include the plus or minus. And since these are asymptotes, it is best to list them separately. Let them each have their own equation, because that's what's going on. It's not a value. They're equations of lines, and so they should be separate. All right. Let's do one more. I'm going to bring up this correlation here. I want both of those on the same page. There we go. So if we look at our vertical asymptote, our denominator, set equal to 0 and solve. X equals 3. For our horizontal asymptote, notice the degree of the denominator is less than the degree of the numerator. No horizontal asymptote. That would be our answer. There isn't one. But check this out. Suppose we actually divide these, and we write our answer as quotient plus remainder over divisor. If the quotient is equal to k, then we'll have a horizontal asymptote. If the quotient is equal to a linear expression, then we have a slant asymptote. So let's take a look at that. Let's use synthetic division. If x minus 3 is the divisor, 3 goes in the little box. 1x squared, 0 x's, and 7. Drop the 1. Multiply to go up and over. Add straight down. Multiply to go up and over. Add straight down. 9 and 7 has always been 16. So this is our remainder. Here's our expression. This is 1x plus 3. So it turns out we will have a slant asymptote of y equals x plus 3. And we can see that here in our graph. Let's graph x squared plus 7 divided by x minus 3. I'm using parentheses because my calculator is only as smart as I make it. So we can't see the other portion of the graph. It's too far up here. I could zoom out real quick. So what I'm suggesting, I'm flat out telling you, is that if I graph the line x plus 3, and let's go ahead and make that a dotted line. Come on, you could do it. Dotted line. There we go. We can see that as x goes to infinity, f of x follows this line. As x goes to negative infinity, f of x follows this line. So a slant asymptote is a horizontal asymptote that's been slanted. So very similar. And this division algorithm is a great way of finding your slant asymptote, or if there's no x's, or if there are no x's remaining, it'll give you your horizontal asymptote as well. All right, I'm going to stop here. I'm going to make this a part 1 and a part 2. I see this getting away from me if I keep going. So I'm going to stop part 1 here, and I'm going to pick up part 2 on the next page of the notes.